Now let's consider the form of the reaction rate. So if I have some reaction, A plus B gives product, then in general, many reactions follow the following type of form. The reaction rate is equal to a constant, which we call a rate constant, times the concentration of A and the concentration of B multiplied together. So I take the reactants and I form a product with their concentrations and raise them to some power. Now this A and B is not necessarily the stoichiometric coefficients in the reaction. We'd have to determine little a and b by experiment. So many reactions can be written in this form, where we just take the reactants concentrations raised to a power and multiply them, and then we have a proportionality constant here called a rate constant. Some reactions are much more complicated, and so you can't write down this simple form, but many reactions you can, and so we'll use this form for the reactions in this class. So say I have a reaction, 2A plus B gives products, and I want to write the rate in some form, and I'll use this general form where I take the concentration of the reactants and raise them to some power. Now A is not necessarily 2 and little b is not necessarily 1. We have to do experiments to determine what little a and b are. So here's an example of how to do an experiment. Say we make a table and we have concentration of A, concentration of B, and the rate of the reaction. And so we do several experiments. And so say we start, this is experiment 1, 2, 3. So say we start with the concentration of A of 0.1 molar and the concentration of B at 0.1 molar. And then experimentally we measure the rate of the reaction, how fast product is formed or how fast one of these reactants disappears. So the rate, say, is 3.0 times 10 to the minus 2 molar per minute. So that is our rate. And you can see the rate is concentration divided by time. And then we do another experiment where we say double the concentration of A, but we'll keep the concentration of B the same. And then we measure the rate. And say we measure the rate at 6 times 10 to the minus 2 molar per minute. And then we double the concentration of A and B, and we measure the rate, and we measure the rate as 3.6 times 10 to the minus 1 molar per minute. So this will allow us to find the exponents A and B. So here we doubled A, but we kept B the same, and we want to know how it affects the rate. So we're doubling A, so we're increasing A by a factor of 2. So 2 to the A is equal to the increase in the rate. So we double A, keeping B the same, and so the rate doubles. So 2 to the 1 would double the rate. Now here we have a rate, and we double B, and we see that the rate goes up by a factor of 4. Great. goes up by a factor of 4. So if we double b, 2 squared goes up by a factor of 4. So we can tell these exponents by constructing a table like this and doing experiments. Now, if I made these easy so that we could do it in our head. So what if we couldn't do it in our head? What if you didn't have, doubles here? What if you went up by a factor of 1.6 and the rate would increase by some factor, and so it's not easy just to glance at it and find out the exponents a and b. So what could we do? Well, we can take the ratio of the rates for 2 different experiments. So, oops, this is supposed to be a 1. So here we have the rate for experiment 2, which is this. So this subscript means experiment 2. And then we have divided by the rate for experiment 1. So this subscript means the concentrations of A and B in experiment number 1. So between experiment number 1 and 2, we increase the concentration of A, but we keep the concentration of B the same. Therefore, B for experiment 2, B for experiment 1 are the same, and so they will cancel. So now we just have the ratio of the concentrations of A. So I can write this as, and you'll notice that the rate constant cancels as well. So now I can write this as the concentration of A for experiment 2 divided by the concentration of A for experiment 1 raised to the little a power, and I can factor out the power like that. So now I have the ratio of the rates is equal to the ratio of the concentrations raised to the little a power. Now if I have an unknown, I'm trying to find little a, if it's in the exponent, I can take the log of both sides of the equation and use the identity of logarithms to get a out of the exponent. So I'll take the log of both sides of the equation and using a property of logs, if I have an exponent in the argument of the log, I can write that as a coefficient in front of the logarithm. So this becomes a log concentration of A for experiment 2 divided by the concentration of A at experiment 1. So now I can easily solve for little a. So little a is equal to the log of the ratio of the rates over the log of the ratio of the concentrations. So I have experiment 2 and experiment 1 and the rates for those, and I have the concentration for experiment 2 and the concentration for experiment 1, and so I just take the ratio of these logs and that'll give me little a. Then I do the same thing for B. I take the ratio of the rates and find an experiment where A doesn't change but B does, and then A would cancel in the equation. So I have rate 3, say, over rate 2. And say between experiments 3 and 2, the concentration of A doesn't change. So it will cancel, the rate constant cancels, and then I'll just have so I'll pick 2 experiments where A doesn't change concentration, but B does, and then I can solve for B, just like I did with A. And that will give me little b. So this is how I find the exponents in my rate expression. So if I have this reaction where I have reactants A and B giving products, I can't just use the stoichiometric coefficients for these powers. I have to find them experimentally, and so this is the way I can find them experimentally. And then once I know these coefficients, then I know the rate expression.